So this is 6.1 Introduction to Vectors. We're going to start by talking about what a vector is. Okay, up until now you've been dealing with quantities that are known as scalars, right? So things like what you do in algebra, right? Temperature, mass, distance, and speed are applications of such things. But here we're going to look at vectors which have a magnitude and direction, right? So scalars are just magnitude, but vectors have both quantity that have both magnitude and direction. So we can represent a vector using an arrow called a directed line segment. It looks like what you see here on the right. Tail of a vector with at the tail of the arrow, and the head of the vector where the vector is pointing to in its direction. And then we deal with vectors by using notation such as this with a letter, and then with an arrow above the letter. Okay. The length of the arrow that you draw for the vector represents its magnitude, and typically we sometimes use scale drawings, but we're not going to be using scale drawings so much. And the arrowhead just points again in the direction of the vector. So some examples we can use or to do to express a vector would be something like, looking at part A, let's still draw a vector to represent a velocity, right? When I say the word velocity, I don't mean speed, right? Speed is just a magnitude, but a velocity is a speed with a direction. If you take physics, you might be aware of that. Okay, so I can represent a velocity as a vector. And so if I want to draw a vector that's 40 kilometers northwest, NW means northwest, I can draw a compass system north, south, west, east, and then draw a vector pointing northwest. And you try your best to, when you say northwest, it's exactly halfway between the north direction and the west direction. And so there's my vector, okay? And I can write it as vector D, or many other letters really, but here we're asked to write as vector D. Weight is also a vector, right? As opposed to mass. Mass is just the amount of stuff in something. Weight is the influence of gravity acting on an object. So the weight is a vector because weight points downwards. 200 Newton weight pointing downward be an example here. Okay, and I can also use coordinate points to represent a vector. So if I had a coordinate point, let's just scale this one grid square as 1. So point A is at 1, 1, and the point B would be at 3 on the X and 4 on the Y. So up here, so there's point B, down here is point A, and I can connect those 2 points with a line, and there you go. There's your vector, and if it's written as AB with the arrowhead on top of it, then that means the arrowhead has to be at the B. So the vector starts at the first letter A and ends at B. Okay, some vector notation that you're going to encounter. So UV are vectors. Some textbooks will just use bolded letters, but we're not going to use bolded letters. Okay, so let's try and avoid that because it's hard to read. How do you really? You're not going to take time to bold your letters when you're writing out vectors. So use U and V with the arrowheads on top. What you're used to is writing letters as scalars, so variables as scalars or parameters as scalars, A and B. So that still remains the same. When we're talking about just the magnitude of the vector and not the direction, just the magnitude only, we're going to use absolute value signs. Okay, so you can see these absolute value brackets, these straight vertical brackets that are a little bit lengthy. Okay, and if we're talking about a vector between 2 points, then A to B, write the 2 points, the vector that starts at point A and ends at point B. Okay, so classifying quantities as vectors or scalars. If I look at 24 meters squared, that's an area, okay, and there's no direction there. That's going to be a scalar value. If I look at P to Q, we have a vector value there. If I look at PQ with the absolute value signs around it, that's going to be a magnitude. So even though there's a vector inside, I'm specifically using the brackets to show, hey, I only want the magnitude of that vector. So that's going to be a scalar value. 15 degrees Celsius, that's a temperature. Okay, that's going to be a scalar. And then, if you have a vector and a minus vector, that's kind of a way of saying let's change the direction of the vector, but it's still a vector. Okay. And what we also have to know is some angles. How do we get some angles here? Different kinds of systems to measure angles. We have true bearings. Okay, a true bearing is just a compass measurement where the angle is measured from north in a clockwise direction. So you start at due north, right? That's going to be 0 degrees, and you go in a clockwise direction. So I can draw a vector at a bearing of 295 degrees. So when you see this bearing of, that's denotes a true bearing. So 0 degrees, all right, so I have to start here, and then I'm going to go around this way. So if you know every quadrant represents 90 degrees, okay, so I want 295. I have to go clockwise, right? So I have to go clockwise. If I reach here, down here, that's 180 degrees. If I reach over here, it's another 90 added to that, so it's 270. And then 295 would be about 25 degrees more. So here somewhere, I'm just estimating, really, it's not really exact. So 25 degrees more, that brings it to 295, okay? So there is your angle at a true bearing of 295. And remember, it's clockwise, so you have to go clockwise like this, okay? Okay. Another example, we can draw a vector at 2 kilometers at a true bearing of 60 degrees. So 0, 6, 0, sometimes true bearings are written with 3 digits, so you'd have a leading 0. But otherwise, hey, it's 60 degrees. Start from true north, okay? And we're going to draw a vector over here. That is going to be 60 degrees going clockwise from true north. And let's label that vector D. Okay, I didn't label the other one, did I? Vector V. Okay. Quadrant bearings is another kind of example, another kind of angle measurement we're going to use, and maybe commonly found in your physics classes too. So quadrant bearings require the whole compass, north, south, west, east. Okay, and it's written something like this. If I draw vector V at 4 kilometers in its magnitude, and here's the bearing, north 80 degrees west. Okay, north 80 degrees west. So what that says is you start at due north, you swing 80 degrees toward the west. So go toward west. So you start at due north, you swing toward the west. Sometimes you start at due north and you swing toward the east, but no, here we're swinging toward the west. Okay, so this angle here is 80 degrees. Okay, so always make sure when you're doing these kinds of quadrant bearings, the first number is either going to be north or south. You have to start on the north-south line. You can never start west or east. Physics may allow it, but here in our conventions for our math book, math course, it's going to be north or south. Okay, so here's to draw another vector from 2 kilometers south, 70 degrees east. So here's south, north, east, west. Start due south, swing 70 degrees. Oh, that's not toward the west. Okay, we don't want to do that. We want to swing toward the east. Okay, so there's a vector. I don't need this line down here. Okay, and so you start south and you swing toward the east 70 degrees. That's your vector. Okay, and that's how you use a quadrant bearing. Sometimes we'll need to know how to convert between true bearings and its equivalent quadrant bearing. Okay, so think, hey, 65 degrees. If I'm given the true bearing, what's the quadrant bearing? So 65 degrees always starts due north. Here is 65 degrees. Oh, okay. How do I write that as a quadrant bearing? Well, we're dealing with the northeast quadrant, right? So that means we're going to write this as north. Always start north or south on the north-south line. So starting from the north, okay. So we're going to swing 65 degrees toward the east. And that's how you visualize it, right? So if you're in that first quadrant, if you're in the top right quadrant, it's just always going to be the north and whatever the true bearing is toward the east. Okay. What about 120 degrees? Well, 120 degrees would put you in this quadrant here, right? Right? Because remember, you start from due north, you swing 90 degrees, and you swing a little bit more until you reach 120 degrees. That's going to be 120 degrees. So how much more do you swing here? That's going to be 30 degrees more. Oops. Okay, and then you have, well, now you have to draw the equivalent quadrant bearing. So remember, you have to start from the north-south line. Okay, but we're not going to start north because north, you cannot say north 120 degrees toward the east. That does not work. This angle here has to be a number that's less than 90. Okay, so we're going to erase that. Instead, we're going to start from due south and swing this way. how much do I swing that way? Well, if you know the whole shape here is 90 degrees, then 90 minus 30 is the answer. So 90 minus 30, so this angle here is 90 minus 30, which is 60 degrees. So south, 60 degrees, swing toward the east. Right, that's the east. So you're swinging toward the east, not the west. So in general, if you're in the bottom right quadrant, then your quadrant bearing is going to be south 180 minus the true bearing toward the east. That's kind of a general formula because, right, you know, remember, so another way to do this is that, hey, you have a 180 degree line and if you know your true bearing is 120, you could work out the 30 if you want, but the quicker way of doing it is just say, hey, take the 180, subtract the 120, and you get 60, right? And that's an equivalent way of doing it. But you don't have to memorize the formula, just visualize this. Visualize this and you'll get it, okay? 235 degrees, that puts us in the bottom left quadrant, right? So starting from due north, you swing 190, 180, and then whoop, all the way to 235, okay? So there's 235 degrees. Draw your quadrant bearing south. We're going to be in south, swinging toward the west. At what angle? Well, I just need this angle right here, okay? So if I took the true bearing and I subtracted 180, I'll get that angle, okay? So south, take the true bearing, subtract 180, and you're swinging toward the west. Okay, so what's the true bearing? 235 minus 180 equals 55 degrees. So south, 55 degrees west is your answer. Okay, 310 degrees, that puts us in the upper left quadrant here. So again, starting from due north, the true bearing means go all the way around. Okay, that's 310 degrees. All right. And in terms of quadrant bearings, so north, south, west, east, where are we going to be doing? What are we going to be doing? We're going to be in the north. Start on the north-south line, so it's going to be due north. And we're going to swing this way toward the west. How many degrees will we be swinging? Well, if you took the true bearing and you subtract, sorry, not the true bearing. If you took 360, right? If you go a complete circle is 360 degrees, right? If you took a 360 and you subtract the true bearing, you'll get the answer, right? So if we know the true bearing is 310, the missing part is just subtracted from 360. So 360 minus 310 equals 50 degrees. So north, 50 degrees west. That's your quadrant bearing. Okay. We can also go the other way around. North, 40 degrees east. So if there's north, here's east. 40 degrees north, swinging 40 degrees to the east. That's going to be the same thing as your true bearing when it's in the first quadrant like that. So your true bearing is 40 degrees. South, 65 degrees east. So south, swing 65 degrees toward the east. What is the true bearing for that? Well, you have to think about it. Okay. Well, the true bearing really is from due north, going clockwise to that vector. Okay. So if you know the whole north-south line is 180 degrees, I go 180 minus the 65, and I get the answer, 115. There's your true bearing right there. So this is 115. Okay, another example, south 32 degrees west. So here's the south line, here's the west line, here's 32 degrees. Okay, and, okay, so what's the true bearing? The true bearing is from due north, going clockwise all the way around. So I know I'm going to go 180 degrees here, and if I add 32 more, I'll get the answer. Okay, that's going to be 212 degrees. North, 27 degrees west. Now here we are in the top left quadrant. North, going to the west, 27 degrees. How do I find the true bearing? Don't say 27 degrees. Remember, it's complete go clockwise all the way around. So if I have to take the full 360, subtract that 27, and I'll get the answer. It's going to be 333 degrees. So this true bearing is 333 degrees. Okay. Equal vectors. Vectors of the same magnitude and same direction. Location of the vectors does not matter. Okay. When I come back to you in class, I'll talk more about that. But it just says, hey, all three vectors, they have the same length of the arrow. They're equal in magnitude. They're pointing to the right. They're all the same direction. So they're equal vectors. It doesn't matter where you place them in a 2D space or a 3D space. They are still equivalent vectors. Opposite vectors just are two vectors that are the same magnitude. So you notice they have the same size, okay, but they're pointing in opposite directions. One's pointing left and the other one's pointing right. Those are opposite vectors. And the way we denote them is by using a negative sign, okay? So the opposite of AB can be written as negative AB, or you can just write it as the vector starting from B and ending at A. That's also equivalent. So there's two ways of doing it, okay? If you're using single letters, so vector V, the opposite vector would be negative V. Okay, parallel vectors. Parallel vectors are vectors that have the same or opposite direction, but not necessarily the same magnitude, okay? So these vectors are parallel, but they don't have the same magnitude, right? A to B, C to D, okay, different size vectors. So with this example, can we give some examples of vectors that are equal? So yeah, we can create a vector from A to B and then create a vector from E to D. Those are equal. A to B is equal to E to D. What about two vectors that are parallel that have different magnitudes, right? So, well, we have parallel but different magnitudes. So we have maybe this vector here and this vector here. So I can create a vector from C to D and one from B to E. So B to E and C to D. Okay, equal in magnitude but opposite in direction. Let's erase the board a little bit here. Equal in magnitude but opposite in direction. So I can create the vector A to B and D to E. They're equal in magnitude, the same size, because it's a regular hexagon. All six sides, outside sides are the same length. But I'm just making them in such a way that they're pointing in opposite directions. So A to B, the vector from A going to B, and the vector from D going to E. Okay? And what about equal in magnitude but not parallel? Okay, well, let's just pick two different sides of the hexagon, right? There's this side here, regular hexagon. Those sides are the same length, but they're not parallel. So I can say A to F and A to B. Okay, there's your quick lesson for 6.1. Have a look at the examples, exercises, and if any questions, we'll come back next time and talk about it. All right.